Let me give a graphical illustration. I know that this concept theoretically can be a little bit confusing. So what we're doing is the following. We're looking for this function y equals f of x, but remember, in reality we don't have that function. Okay, that's our goal, but we're trying to build it up. What we do have, however, is some initial value x0 and corresponding to which we know what the corresponding y value is. Okay, so that's our first point, x0, y0. Now we use a linear approximation. Remember, that means constructing the tangent line at that point, and then instead of figuring out the value of the function at the next number x1, we're going to compute the value of on the tangent line of this new point. Okay, so this gives us a new point, which, as you can see, is a good approximation of what we would get on the original function. Not quite equal to it, but a good approximation. Now, how do we continue from here on? Here is a really important point, because at this point we're going to forget. Well, first of all, at this point we're going to write down the new coordinates of the second point, but at this point what we're going to do is we're going to forget about the tangent line, because that tangent line was useful in order to move away from x0 to x1. Now what we need to do is we need to repeat the procedure on x1. But remember that now if I'm looking for a solution of the original differential equation with this new starting point, I'm not looking at the same function as before. I'm looking at a different function, okay, which is going to be probably very similar to the one before, but it's a different solution. It's not the same solution as before. Remember, the differential equation will have infinitely many solutions. And so if I change my initial value, that's going to change the solution. However, it's still a solution which is close by. So what I'm going to do is I'm going to repeat the same process. I'm going to construct the tangent line. I'm going to move away to the next point, x2. I'm going to figure out what the value corresponding to x2 on this new tangent line is. That is going to be my third point. Then I write down the coordinates of that third point on my table, and I start all over again, which means I'm going to forget about the second approximation and the second tangent line, and I'm going to have to solve the differential equation starting from this third point. That means once again I'm going to have to use a different solution of the differential equation, and you can see where the problem is here with this process. It's not a huge problem. We're going to see in applications that this method works actually fairly well for many interesting differential equations, but it is a theoretical problem to keep in mind. But at this point, again, we'll continue as before. We're going to construct the tangent line. We're going to pick up the point nearby the x3, and we're going to figure out corresponding to it what the new point and what its y coordinates are. So this is the visual idea of what this method works, how this method works. Notice that there are a number of approximations here. Not only we're approximating because at each step we're going along the tangent line, but we are also approximating because after the first step we're not even working on the original function, because of course we don't know what that function is. That's the whole point. We're trying to figure out what it is. And so we have to be careful on how we set up our approximations and how we set up the whole procedure. Let's go back to the algebra, to the theory of it. Okay, so how does this method work on paper? Okay, so first of all, what we're going to do is we're going to keep going as much as we want or need by using this formula. We're going to compute the next y value, f of xn, by using the previous y value, yn minus 1, the previous step, and then computing what the slope is at that last point that we figured out, multiplied by h, and that will give us our yn minus 1. Okay? So notice a few things here. Okay, the step size h represents the increment in the x value. It tells us how far we want to move from one point to the next along the x-axis. Okay, so that's our, if you want, the delta x that we have used also in the past. Now each estimate gives a point on the tangent line, not on the curve. And as once again, just to repeat, because this is a very important point, at each step we're actually even changing the curve. Okay, so we're approximating the curve itself. That means that the more iterations we do, the further away we are going to go from the true solution. So that means that when we're applying this method, we want to make sure that we don't use too many points in order to construct our solution, just as many as we need in order to get whatever information we need from the ODE. The other thing is also the larger h is, the further away we go from the true solution. If we use a small value of h, then each one of those tangent lines stays fairly close to the original function, and so as we move from one point to the next, we're actually not going to stray very far away from the original curve or from whichever curve we're using. But if we use a large h, then we may be taking some really big steps and sometimes end up really far away from the actual solution. Some more considerations to keep in mind. Okay. First of all, Euler's method is computationally intense. There is lots of calculations to be done. Even though I said we don't want to use too many points because the more steps we take, the further away we go from the solution. But if we take h small enough, we can actually repeat the procedure many times. And of course, with computers these days, it's reasonable to ask a computer to do maybe 1,000 iterations, okay? But that's exactly the point. We want to use a computer program to make it efficient. You don't want to do this thing by hand, even though originally when it was developed, it was used by hand. But you can imagine the complexity of the calculations. Also, what we can do is we can, as we compute these solutions, you may want to plot the points just like I did in the original graph to get a feel for the solution. Quite often what we're looking for in real applications is not so much the numerical estimates, but we want to get a feel for what the solution looks like. Is it concave up? Is it concave down? Does it change a lot? What kind of features does it have? And so for these kind of questions, plotting the points that we obtain can be very useful. Another thing we can do once we have a plot of the curve, of the solution curve, is that we can get a feel for what kind of error we're making, which way the approximations are going. We're going to go back into that in a minute, but keep in mind that this is something that is can be done. So in other words, a lot of this method provides qualitative information rather than quantitative information about the solution. But in many cases, as you're going to see in the next years, not in this class, that can be enough information to be extracted from the differential equation.